Hello. This videotape is going to cover the operation and construction of the plasma tube beam ray device and its effects on some selected microorganisms. At the moment, what you are looking at here is a phanetron diode in operation. And it's going to shift frequencies here, just like that. And as it does, you notice the plasma became a little more intense and a little brighter. And we moved from about 700 cycles to about 7,000 cycles. I'm going to try and let you listen to a little bit of that for just a moment. Is partially formed from an electrostatic field around the tube and also comes out of the CB unit. This is an overview of the device itself. At the bottom right we see the linear amplifier, on the left is a CB radio and the power supply. Coming up is a function generator. This is a Kinnaman unit and it allows one to sequentially output 19 frequencies simply by pushing a button. This is our antenna tuner by MFJ, and currently it's tuned at about 1.6 or 7 to 1 SWR. Behind is the plasma tube. This happens to be an argon-filled quartz tube. This is the oscilloscope tracing of the device in operation. And what I did was place a probe about 6 feet away from the device while it's running. And I've switched audio frequencies, and I've moved from like 700 to 800 to 900 to 1,000 cycles. And as I switch frequencies, you'll see that the pulse narrows and becomes more frequent. This is my dark field microscope, which is a combination of parts from other microscopes, but primarily it's an Alsgena. This is a 100x objective, and in a 100x objective you need an internal iris diaphragm, and the little ring I'm turning there is for the diaphragm. This is what's known as a cardioid or catioid type of dark field condenser with a little mirror on the bottom. This one happens to be made in Russia, and it's by LOMO microscopes. Here's our little mirror. Now what the device does is it produces a wave that is easily accepted by cellular organisms. And at the right frequency, the organism will accept the wave and begin to vibrate. Just like that. This particular pond water organism, it's a little protozoan, has a frequency that it is currently responding to of 8,296 cycles. And you can see it's pretty well shaking him up. If you ran another frequency, this would not happen. Now, if you let this organism be exposed to this frequency for long enough, it will eventually die. It does not explode, it just dies. Just basically shakes it to death. If one were to take and turn the device off after about a minute of exposure, the organism continues to shake like this for about another 2 to 3 minutes. And providing it has not been killed at that time, it will basically go back to swimming in its prior to being agitated state. This structure was found in the blood of an individual that has an elevated PSA level, which relates to the prostate. It was undergoing exposures to the device, and this was found in the blood after one of the exposures. In my volume 1, there's quite a bit of debris in the blood of one particular individual that's shown on the tape of cancer cells that broke down from the effects of the device. Whether this structure is from a cancer or not is unknown. This is a Blepharisma protozoan organism. Normally, they are highly motile and swim around the slide quite freely. At the moment, this particular organism is under the influence of the wave and is undergoing a disintegration process. Its interior is basically disintegrating. A Blepharisma generally is a complex organism. In this case, most of the interior structure is being destroyed by the device. In a moment, the actual cell wall will rupture. As the organism disintegrates, most of its internal structures just break down into these small little particles. And one of the interesting phenomena that happen as the breakdown occurs, that these kind of globule-like structures form with all these little particulate pieces in them, such as this large one here. A little later on in the film, we'll show you a similar analog to this that was found inside my mouth. But the difference is that it actually happens to have a nucleus and is reproductive. This is another freshwater protozoan, and it's now under the influence of the device. Normally these, again, are highly motile. And this particular fellow will undergo an osmotic change with its body structure and basically just fill with water and explode. This fellow's MOR was 1,050 cycles. By the way, the blepharisma has an MOR of 927 and 3,050 cycles. This is another similar type of organism, just happens to blow up a little faster. I'm sorry for the loss of detail. This happened on the transfer from my master tape. This is a bacterial contaminant found in a culture of group D streptococcus. More than likely it's Strep faecialis. What we're going to see here is the effects of the device on this microorganism. It will move from a semi-coccoid shape, round that is, to a very granular, thin rod, but yet still be arranged in chains. Here we can see something of the beginning of the transformation process. Down in the lower right-hand corner, you can see how granular some of these individual cells are becoming. This occurred over about a 45 to 50 minute period of exposure, by the way. This transformational process is known as pleomorphism, where an organism can be shifted from one shape to another and yet still be the same organism. Here we can see exactly how granular some of these are becoming, but also notice how rod-like they're becoming too. And this is the same organism that we started with. It's known as inverse video, where the blacks become white and the whites become black, and it gives something of a depth effect. What you're looking at now is the final shape of the organism after plating and letting grow for one day. You can see it's become very rod-like, still maintains a lot of granularity, but it's changed quite drastically in shape from its original coccoid form. Now this is some actual group D strep. We're going to watch what happens as the wave affects it. Again, this is inverse video, but you can see how things are starting to kind of join together. They've kind of formed pairs instead of being individuals. Now this is after exposure for about an hour and then plating for 1 day. If you notice, some of these are no longer really all that round as a normal streptococcus would be. Some of these look very rod-like. Some of them are somewhat transitional shaped, and some are completely unchanged and are still very normal-looking streptococcus. Now these are E. coli. If you look carefully, you'll see some little black polar bodies on the end of some of these organisms. The significance of these is this. Dr. Rife believed that these little black polar bodies in some microorganisms were responsible for disease. More specifically, Dr. Rife claimed that from some organisms, these little black bodies could cause cancer. The problem is, of course, being dark field, once the little black bodies are released from the bacteria, you can't see them anymore. These bodies are apparently also unstainable, which is why Dr. Rife used a light staining method. This is a paramecium under the effect of the device. And if you look in the upper right-hand corner, it's now undergoing a cell wall rupture. This occurs at 1,150 cycles. As the disintegration process continues, basically the whole internal structure of the paramecium breaks down and falls apart. Essentially, there's not much left of the paramecium. This, too, is another freshwater protozoan under the influence of the wave. You notice one of the first things that happen is that it loses its mobility. Here we see a cell wall rupture and evisceration of the organism's protoplasm and other internal cellular structures. Another pretty obvious cell wall rupture with almost a blister-like formation. This is from the effect of the wave on this particular paramecium. These are common, what are known as turbatrix, or vinegar eels, as the case may be. And this is the effects of the device running at 104 cycles. Normally these are very active swimmers, moving in a very undulating snake-like manner. Now remember that globule that formed when the blepharism blew up? Well, these were found inside my mouth. These are normal constituents, found at least in my mouth. As you can see, they have a nice nucleus. They look very similar in many ways to some of those little globules that were formed. Just a curiosity. This is a Cobra, model 19. And this is the bottom of the CB. All the bottoms of the CBs or tops have this grill-like opening for the speaker, and that's a side on all of the devices or CBs that you will remove to access the electronics. What we're doing now is removing the back surface of the speaker in order to remove the wires off the little microphone on the inside. Here you see the two wires that are connected to the microphone. This is standard in all of the microphones of all three CB units that we use. In some manner, there's a little microphone about this side in all of them. Now these two wires attached to it that must be removed with a soldering iron. You just heat the wire up and remove it. What I do is place a small scratch pad underneath with the cardboard side up. It's just something to keep heat from getting through and melting the plastic, and a nice surface to work on. Apply a little solder and heat to an eyelet, and we solder up our wires we just removed from the little microphone. Now, this is where you're going to put the holes. You're going to drill into the microphone itself to mount the eyelets. Here we are doing a little drilling. And now we have our number 6 screws, either 1/2 to 3/4 of an inch long. We're going to insert through the holes we just drilled, like so, with our eyelets, and secure down our eyelets. Very simple. Then all we have to do is add back in the little nuts to secure at the front. Notice there's a pivot point on the microphone key. All microphones have this. Make sure you reinstall the pivot point properly back in the case and then test it so that the key will close properly and spring back. Inserting the lid back on, one must make sure that it is properly secured all around the outside of the microphone so that the gap is even. And be sure and test the key to make sure it doesn't bind. What we're doing here is testing to find out which one of the two connections is positive. Now the negative side will cause a connection to be made to the ground, and so that would cause the multimeter to make that tone. So what we do is we mark the microphone as just shown with a little positive on the opposite side where it doesn't make the tone. Now what I'm doing here is I'm showing that the output of the CB is about 4 to 5 watts here, and I have it set on the internal dummy load, and I'm showing how changing the antenna match and the trans match buttons shifts what's called the SWR. And you want the SWR to be down at the bottom, just like that, with the needle on the right-hand side of the meter, and the needle that reads on the left-hand side of the meter to be as high as possible. And there I go, the key and the power is off. Now we're removing the top cover, or bottom cover as the case may be. And this is RV2. And what we're going to do is we're going to take a little screwdriver and we're going to take and turn that RV2 in a counterclockwise manner as far as it'll go, just like that. And that completes modification of the CB unit. Now what you can see is that the unit produces about 10 watts of output. And we've done that by using induction setting L, and it's been over on the dummy load position. Now here we have a very small plasma tube that I am putting a modulated wave of about 700 cycles into the CB with. And we've lit this tube up, showing you that you can actually light these small tubes, as in the lower power unit, with just a citizens band radio that we just modified to overmodulate. There, the tube's off. Now if you watch, we key up, the two needles cross at a high level, approximately an SWR of 3, and then it's brought back down, in this case by turning the trans match button, bring it into light, and then bringing the SWR down. Again, needle on the right as low as possible, needle on the left as high as possible. Now this is showing the difference in changing the applied audio frequency. Here we've got 492 cycles. I'm going to turn up the power and watch what happens to the needles on the SWR meter on the tuner. You can see it actually climbs up a little bit, starts modulating more power. I'm going to shift by a factor of 10 here by punching this other button, and we're going up to about 4,700 cycles. And what I'm doing is I'm kind of peaking the meter. You can see it's making almost 20 watts now up here at this 4,726 cycles. now going to modify the Maxon MCB30. And again, you can see the little waffle holes on the bottom for the microphone, and that's the side we're going to pull off of the unit to access its interior. Going to take our screwdriver here, and we're going to turn RV2 right there. Fully clockwise, just like that. This is a Maxon microphone, and we're going to modify it just like we did with the Cobra 19 and put those two little screws on it and mark the positive side in such a manner. Only the negative side makes the tone. The positive side you should mark. Now we're going to modify the Uniden 510XL. And the first thing you have to do to the Unidin's microphone is you have to remove this little label on the outside of it with a knife. Be careful, don't cut yourself. But it's made out of aluminum, and that's where we're going to mount the screws. In this case, the screws are going to mount on the front of the microphone. There and there. Now inside the microphone there's this large metal plate. You must remove that by removing that center screw as such, and out it comes. And then we have our standard little microphone in the center. We have to remove these two wires from the little microphone speaker as before, using a nice soldering gun, just as such. And to those we'll attach our eyelets as we have done previously. As you can see, there's a problem here. The Uniden does not have a direct ground. So what you have to do is look on the inside of the microphone, and there's a wire that's unshielded cable, just stranded copper, and that is going to be the ground side. So the opposite connector is going to be the positive connector that you will attach the positive side. We're now going to cut diode D14. This is marked on the circuit board. And I just use a pair of scissors to do this. You really don't need a specialized pair of electronic parts cutters or wire cutters. This will work just fine. Right there, one end is cut. It's hard to see on the video, but it's been done. I'll try and pull it up here for you. There we go. And that would be a good idea just to keep that from possibly shorting back out to the shorted end. Now we have to cut R93, and that's rather difficult to find. You're going to need a magnifying glass to get in and find that resistor. Make sure you get the proper one, but in this case, that's right there. Make sure that you're on the right resistor before you cut that. And again, you can use a pair of scissors to do this. I know it's hard to see here, but this has been cut, and right there's R93. Again, move the resistor slightly out of the way so it doesn't make contact with any other loose wires. Now this is a Lodestar audio generator counter. What I'm doing is showing that it's set on 80 cycles, and as you punch each button it goes up by a factor of approximately 10. So we started at about 80 and now we're up to 78,000, and then we're back down here to 788. So this is a minus dB button. There's two of them, one's minus 20, one's minus 40. You want to keep the minus 20 in. This button controls the output voltage, and then there's a square wave and sine wave function. You want to keep that square wave button pushed in at all times so that we generate square waves. All you do to attach the BNC cable is put it on and give it a half twist, and it secures itself. You want to keep this switch all the way up to internal. Otherwise it acts like a counter that'll count something you might say like any frequencies external to it. You put an antenna on it even. You want to keep the button pushed in for square waves. This is a digital multimeter, and if you notice there's a red and black cable. These are all standard. Put the black cable in the common output and the red cable in the volts, ohm, amperes output. Attach the red alligator clip to the red probe and the black alligator clip to the black probe. Now, what we do is we set the meter on the AC scale, turn it down to about the 2 volt scale in this case. And we're turning the meter on. It shows in this case I've got about 276 millivolts outputting from my Lodestar audio generator. Now by turning the little knob here, we can turn the voltage up, if you watch the meter, up, and then we can turn it back down. You want to set it to 200 millivolts, or right thereabouts. Somewhere generally it winds up between 9 and 10 o'clock. Notice by changing the frequency, the millivolt output changes just slightly. This has to do with the fact the meter is set to read at 60 cycles versus 70,000 cycles like we show here. You should set your audio generator to around the 700 cycle range to set your output voltage. Now this is a Kinnaman function generator with the voltage reducer attached. You can see in this case at 1,000 cycles it gives about 203 millivolts. By changing to 700 cycles it still gives about 204 millivolts. And now it's been turned off and back on again. Necessary to complete assembly of the unit. These are some solder-on eyelets and connectors. Got those at an auto parts store. This is some 1/4-inch width braided flat wire. These are standard hose clamps I also purchased at an auto parts store. As you can see, they have a clamping range of about 9/16 to 1 1/4 inch. This is some black number 14 primary wire, also bought at an auto parts store. Some red number 14 primary wire, bought at an auto parts store. This is some 3/16 inch wide flat braided wire, necessary to make ground connections. You can also use this to wrap the tube with. Here we have the back side of a Palomar 225. And this is the front side. There's a power switch, a low, medium, and a high switch in the middle, and a preamp switch. The preamp switch is not necessary. It refers only to the receive mode and amplifies the incoming signal. We're not interested in that. First thing we need to do is pull off about 5 or 6 feet of the red number 14 wire, and we need to strip both ends of this wire by removing about 1/4 to 1/2 inch of the insulation. Just like that. We now attach this red wire to the red power wire coming out of the Palomar 225. Using the soldering gun, we now heat the joint, apply a little bit of solder, and you're going to have to turn this wire over to get it fully soldered. It's a little bit too thick for the solder to flow completely all the way around the wire. Here we've turned the wire upside down. I'm going to solder to the back side, and I've put a pair of pliers over the wire to hold it down in place as I solder the back side. Now repeat the same process using the black wire. After you've made the joints, you need to cover them with some sort of insulator. This is called shrink wrap. By simply sliding this material over the soldered joint and heating it, it shrinks and makes a very tight, secure insulator. You can also just simply use your black electrical tape. It will accomplish the same purpose. Now, using the black electrical tape, we need to bind the two wires, the black and red wire, together so that they just aren't flailing about and get in trouble. So using a small piece of tape, we just about every 8 to 10 inches wrap another piece of tape all the way down the length of the wire to keep the two wires together. Leave about 3 or 4 inches at the end so that you can attach a couple of eyelets, which will then go on to the power supply. That basically completes the Palomar 225. It's now all ready for connection. We're now going to make the wires that will drive the tube. And we take our 1/4 inch wide wire and bend the end and twist it slightly so it's a little smaller, so it will fit on the little eyelet. And sometimes it helps to twist this slightly to catch the wire and bring it up through the mounting hole. You can see it's just slightly through the mounting hole there. Now we just add a little bit of solder, and that completes one end of the wire. Helps to crimp and slightly straighten the wire after everything's all soldered and finished. You can see both wires are of equal length. You want to make sure that they're equal length so that the power that comes across them will be equally balanced. As you can see, the clamp as it comes out of the package is a little bit too big for the tube here in this case, so we're going to have to turn that down a lot closer. You just take a screwdriver and turn it, and the clamp will just tighten right up for us. See how much I had to pull the clamp out. This was only a 3/4 inch outside diameter tube. Most of them that are being made nowadays are 1 inch outside diameter tube. Now what you do is take your wire and wrap it once around the tube and then slide the hose clamp over the top of it. And once in place, secure the clamp slightly. Now there's a problem here in that I put the wire to the inside of the tube. It needs to go to the outside of the tube. This is very important. It allows you to wind the tube, and further it keeps the wires from possibly touching each other and shorting out. And this is a correct method with the wire to the outside of the tube. As you can see, it's not really firmly attached to the tube. Rather, it's just firm enough so you can slide the clamp easily back and forth. Just a snug fit is all you want. There must be some room underneath the clamp for tube expansion. Otherwise, as the glass gets hot, it will expand and crack. Now we have both wires attached to the tube. Helps to either cut the little wires on the end of the tube that drive the electrodes off, or just simply wind them together and bend them over out of the way. We're now going to add eyelets to the power cord on the CB unit. This is basically the same thing as what we did with the Palomar 225 linear amplifier. It helps to have a good solder gun for this. I would recommend at least 70 watts. 100 would be much better. CB radio is now ready for attachment to the power supply. So here we have our modified microphone and our two little eyelets we soldered onto the power cords of the CB radio. And and our tube. In this case, this tube does not need to be wound. This particular tube will just light with the two clamps in place. And our Palomar 225. Now this is the antenna tuner, and we're looking at the back side at the moment. This is an MFJ 949E antenna tuner, and this is a little jumper wire you must put between the wire and the balance line. Now I've used just a small piece of the 3/16 of an inch braided cable, but you can also use a number 14 wire that's left over from when you made your power cords. That must be in place. I'm going to make some insulation here for some of the ground strap. And you cut this just a little bit shorter than the overall length of your ground cable, this particular cable. Now as you can see, only one end of this ground cable has an eyelet soldered to it. This allows you to thread the cable through the insulating plastic hose. Once through, you're now going to solder the other eyelet on the opposite end. Now, on the side of the CB unit, there are a couple of mounting screws. You need to put a washer underneath between the CB and the mounting screw, and then attach the ground cable to one side of the CB. The other end of the ground cable will then go to the linear amplifier. It helps to put a small washer underneath the mounting screw. And we're going to attach the other ground wire, which goes from the CB unit to the antenna tuner. This wire is considerably longer, and read your manual to find out the proper length to cut this. The Palomar 225 needs a cooling fan, and I use a small piece of 3/16 inch diameter wood dowling to place in the 4 mounting holes in the corner of the fan. You may have to drill these holes out to allow the wooden dowels to fit. The idea is to space the fan slightly above the top of the heatsink of the linear amplifier. In the top of the heatsink, you can see 4 mounting holes for the power transistors. This is the area on which you wish to mount the fan. This will be the area of maximum heat generation. You can see this is slightly offset from center. Now I have the completed CB linear amplifier, antenna tuner, fan, our coaxial cables, a short 18-incher and a long 18-footer, your power supply, a 7/16 inch wrench, and the function generator, along with the power strip that will be necessary to make the device operational. First, thread your short cable from the CB to the linear amplifier. Now you can use a long 18-foot cable. It does not seem to make too much difference at this point using this short cable, but it does help limit the amount of stray radio frequency in the room by using this short cable, and therefore helps stabilize your function generator. Now I am loosening the nut for the ground connection from the CB radio to the antenna tuner. We now take the 18-foot long cable and attach it from the output on the linear amplifier that says antenna, and this will go to the antenna tuner. This goes into the connector marked transmitter on the antenna tuner. Now attach the plasma tube to the connectors on the back of the antenna tuner. And that is basically all that's necessary to make the majority of the pieces operate. It's now time to connect the power cords to the power supply. And as you can see at the top of the power supply there's a little positive mark, and we attach all the solid red wires to this positive terminal. Then use a wrench to secure this down, and then proceed on to connect all the black wires, or in some cases there's a red wire with a black stripe. This too would go to the negative terminal. Make sure your wires are in the right place before you ever turn anything on. If you have your wires crossed, you will destroy the instrument. Now ready to turn the device on and get it operational. First thing is to turn on the power supply. Next, turn on your CB radio and set to channel 14. Then turn on your function generator and set it to approximately 700 cycles. Finally, turn on your linear amplifier. Now ready to start the unit, but first we must test it. So we turn the antenna selector down to dummy load, and then key the microphone to make sure that power is coming into the unit. And your both needles should swing up, and you should practice trying to get the SWR level down to the absolute minimum, if at all possible. Once you think you have that knack of getting your SWR set, turn the antenna selector back up to your balanced lined wire selector on the tuned side of the instrument and key the mic. A little luck, your tube will just light right up just like that. Now, as you can see, the function generator output takes a big jump here. It's because it's too close to all the RF. You can see it sitting maybe within about 6 inches of one of the leads there to the plasma tube. It just completely overrides the unit. If you get it a couple feet away, everything is quite stable. Turn the knob up and down, you can notice that the tone goes up and down in the unit. Now, this is the new way of winding tubes. You can see there's a small aluminum reflector behind in a very simple box. I have all of about $4 or $5 in this particular box. You can see there's a clamp on the end and then one more wind out to the end secured with a piece of electrical tape. This technique seems to start most tubes quite effectively. Now, I use screws to secure everything together. This is all made out of 1/2 inch by 4 inch pine board. 2 pieces about 6 feet long. This is a more standard way of winding the tube, using the clamps closer together at the center and then winding outward with about 2 turns to the ends. This is the aluminum used for the reflector. It is 20 thousandths of an inch thick and is freely available at most hardware stores. Here I'm just showing you a measurement of it. The nice thing about this aluminum is that it's easily cuttable with just a simple pair of scissors. Aluminum is also very easy to bend just with your bare hands over a straight edge of a table. Now, I didn't really line this up and measure it like I should, so it's going to come out a little crooked. But I think you get the idea. You get a nice square bend when you do that. You secure the aluminum using some upholstery tacks. These are a little sturdier than your normal thumbtack and can be easily hammered into place through the thin aluminum. If the angle is a little too steep on the aluminum plate, you can always just bend it back out straight if necessary. Now, this is a completed unit here set up in my cart. Now, what's wrong with this cart is it has a lot of metal framework, and we found that it's better not to have a metal framework. It's better to use an all wooden cart, but this lays things out pretty easily so you can see them. The little function generator down below is the Kinnaman unit that is mentioned in the book. It's still undergoing evaluation by me at the moment. Here we see a Uniden 510XL CB, my original linear amplifier, which is mentioned in the book, power supply, microphone, function generator. Here's a little close-up. The little box coming out of the function generator is a voltage reducer. A little better close-up of the antenna tuner and in its standard operating mode. Now I'm going to start the tube, giving you a better idea of what it's like to get a tube started. As you can see, it doesn't always start on the first try, and you have to keep fiddling around a little bit with the antenna match knob. The idea is to minimize the SWR by getting the needle on the left side up as high as possible and the needle on the right down as far as possible. Here we're making about roughly 20 watts. You can see the plasma wave will distort slightly as you get very high SWRs. Leaving your SWR much above 3 for more than approximately 15-20 seconds risks damage to the unit. Here you can get standing waves within the plasma tube. These little balls are standing waves of energy. Here's some more standing waves. See, they'll run forwards and they'll run backwards. This is a neon tube. See, it's quite bright and has a more orangish cast. In this case, changing the SWR merely dims the tube. This is a new commercially available Thanatron tube. It's made in Canada, and the address and contact person is in my book. Price is about $295 US. The instability you see in the plasma here has to do with the fact this is a prototype tube, which has a little too much pressure in it. This will stabilize in just a second. New tubes have a little slightly reduced pressure and don't undergo that instability on first startup. If you look closely on the right-hand side of the tube, you'll see some kind of little spikes standing up. And these are very much like the same spikes that we saw on the oscilloscope at the start of the tape. This is a tube running at about 5 or 6 cycles a second. And this is a tube running at about maybe 2 cycles a second, just to show the effect of the pulse. Here we can more clearly see those modulated spikes on the right-hand side of the tube. Those of you that would buy a Kinnaman function generator, as the Kinnaman unit switches from frequency to frequency, it turns itself off. And as it turns itself off, sometimes the SWR will go completely out of sync into an unacceptable area, such as that. So what I do before I finally turn the unit onto automatic mode is I preset the SWR with the Kinnaman generator outputting and with it not outputting. And as you can see, it takes a little bit of working with the tuner to get this. And generally it's a compromise. You will not be able to reach the lowest absolute SWR by doing this. But once set, it'll be stable at all frequencies, and you won't have to touch the tuner again as it goes through its frequency set. See, here we're moving to 5,000 cycles. You can see the difference between the modulated and unmodulated power level there too, very clearly. 500 cycles. It's holding a pretty steady 1.75 to 1 SWR here. If you have internet access, please be sure and drop by and visit the Rife Technologies site. Email address is rifetech@route66.com.